All right, we're going to look at another type of encryption system that's somewhat similar to what we saw with the Caesar cipher. So this one's called the Decimation cipher. So just like before, we're going to look at our alphabet, put it in a row, right, A through Z, except now we're going to give each of those letters a number. So A is going to be 0, B is going to be 1, all the way up through Z, which is going to be 25. And you can kind of see that in the table that I have down here already set up for us. So those two lines, right, that's going to be what happens every time. Now, you can select any odd number between 3 and 25, except for 13. 13 basically has a problem because it's evenly divisible by 26. So we want to choose some number k that doesn't have any prime divisor in common with 26. That's also why we can't choose even numbers, because 26 is divisible by 2, and so would that even number be. So anyway, we have a lot of numbers to choose from, right? 3, 7, 9, 11, 15, 17, all the way up to 25. And so that value of k is called our key, our encryption key. And so I'm going to show us an example where we use 5, of course, in our activity, and on the project we're going to be looking at things that are different from 5. But this, once you know how it works for one of these keys, you kind of know how it works for all of these keys. So let's see what happens. So in the message, a letter with a numerical value I, so again, that's going to be the second row here. So A's value is 0, B's value is 1. So that's what we mean when we say I. It's going to be replaced with the letter with the numerical value K sub I, modulo 26. Okay, we've actually done some modular arithmetic before. Basically, that's just a remainder, right? If we do long division, modulo 26, that just means divide by 26, find the remainder. That's all that's saying, right? So it's nothing too crazy. And in fact, Excel has a mod function. It will do this for us. So we have done this before. I introduced the mod function. I didn't go too heavy into it, but now we're going to do it a little bit, a little bit further. So if K is 5, then, for example, so these are just two examples to fill out the table here, D is replaced with P. And the reasoning for this is we start with D. We start with D's value. It has a value of 3. We multiply it by our key, 5. So 5 times 3 is 15. We find in this list 15, and we say, oh, 15's over here. And we say, okay, D is now going to be assigned the number 15, which is aligned with P. So D is going to be replaced with P. So we kind of use our numbers here to figure out a path from the initial number to the encrypted or encoded number, or sorry, letter rather. This one did not require modular arithmetic because the product was 15. It was not bigger than 26. So that's fine. But we're going to show an example where like J, where the value of that is 9, right? So J is valued at 9. Multiply by 5, we get 45. Well, 45 is definitely bigger than 26. So we're going to do our modular arithmetic, right? 45 divided by 26, or 45 mod 26. We're going to get this remainder of 19. So we find 19 here, and we go, oh, cool. 19 corresponds to the letter T. So we are going to replace J with T accordingly. So we do this, and in the activity I'm only going to have you do half the alphabet, but let's just kind of see if we can set up a way to do this. So we're going to say, all right, my key is 5. My original number, or sorry, original number, we can put here. And we can say, well, let's say we start with A. So the original number is 0. Then we could do the original number times the key. Well, okay, I can do this pretty smartly. I can just take that original number and say times the key up there. Cool. That's still 0, because, right, multiplication by 0 is 0. And then we want to take that, and you know what, actually, maybe I'll wrap my text here. And then we want to take that and we want to say, okay, well, what about mod 26? We're going to take that number and do, okay, so equals mod. Remember, mod, if we have a number, that's this guy, and our divisor is always going to be 26. So that's still 0. That's kind of boring, right? So this one's 0. let's do our next one though. So if I change this to 1, these are going to change automatically because of the way I set them up. So we get 5, which just becomes 5 here. And I'm going to do 2, and then we'll see what happens with these guys. Okay, 2 becomes 10. 10 mod 26 is still 10, so that's not very exciting. But I'm just starting with some of these, and we say, okay, so A had the value 0. We want its new value to still be 0. So A actually doesn't get replaced. It's still A. B had the original value 1. Now it has the value 5, so we find 5 in this list, and we go, oh, 5 is corresponding to F, so B is going to be replaced with F. C had the original value 2. Now it has the value 10, so we find 10 in the list. Oh, C gets replaced with K. Okay, so those ones where the value doesn't exceed 26 are kind of boring because we said, well, you know, this mod 26 answer is going to be the same as just the original number times the key. So let's choose a different letter here, something with a bigger value. So like M, for example, M has a value of 12 originally assigned to it. So if I say, okay, the original number is 12, I multiply that by 5, the key, I'm going to get 60. But when I do the division by 26, I have a remainder of 8, right? So 60 mod 26 is going to be 8. So I go back over here and I say, well, okay, M has the new value of 8. I find 8 in the list, and I go, oh, okay, in row 2, 8 corresponds with this letter in row 1, which is I. So we basically fill this entire thing out. Now, I'm going to go through here and say, well, there's also some other patterns that we might notice, like for starters, A, B, C, D. When we found our new values, it was 0, 5, 10, 15. We might go, yeah, this is probably going to be 20. This is probably going to be 25. This next one, could it be 30? Well, no, it can't be 30 because that is greater than 26, right? We can't have a modulus that is equal to or greater than 26. So no, that one's not going to work. But if you do find a pattern like this, you go, okay, that's fine. I can start to find those values. So let's see what G would be though. So G originally is 6. And if we let our original number be 6, oh, it turns out it's 4 once we do this little modulus. Let's check 7. Okay, that's going to be 9. Let's check 8. Okay, that's going to be 14. Boy, I don't know. I feel like I'm seeing a pattern here too. So we go from 4 to 9 to 14 to 19. What do we think is going to come next? Well, probably 24 if I'm following the pattern, right? 4s and 9s kind of alternating. But what else do we see? 4 plus 5 gives me 9. Plus 5 gives me 14. Plus 5 gives me 19, and so on. So it turns out we can just, once we have the first number in this sequence, we can keep adding 5. Of course, when I get here, 24 plus 5 is too big. It's 29. It's above 26. That's not going to work. But I can just find the original seed here for this sequence. It's going to be 3. So this goes to 3. And then I go, oh, hey, cool. I already did the next one. So 3 plus 5 is 8. Plus 5 is 13. Plus 5 is 18. Then 23. Then it would be 28, but that's not going to work. Right? 28 mod 26 is actually 2, right? It's got a remainder of 2. So you can certainly check that. You can put that in here and say, again, we're looking at Q is 16. But if we follow the pattern, right, we still get the right modulus. So we say, okay, cool, 2. And now I can just add 5. Add 5, add 5, add 5, and then we would get 27, but that is 1 mod 26. Okay, and then add 5, add 5, add 5. And, right, it would be nice, since we could do this calculation one at a time, boy, wouldn't it be nice to just have some sort of template that does the entire alphabet for us as soon as we tell it the key. Wouldn't that be nice? Ooh, it is nice. I'm actually going to give you that for the project and for the homework. However, I'm not going to give you that for the in-class activity because I want us to kind of work through this idea of using the modulus, using the mod function and going through and kind of seeing what this transformation looks like. So we've done, right, row 3. We still haven't done row 4 here. So we have to take these new numbers, 20, 25, 4, 9, all those things. We got to figure out what letter corresponds to them. So 20, we find that in another spot in the table that corresponds with U. 25 corresponds with Z, right? The last letter of the alphabet. 4 corresponds with E. And again, we're just looking in row 2, saying, oh, there's 4, and then above it is E. 9, okay, look in row 2, there's 9, above it is J. So we have this as our system. 14 becomes O. Oops, not 0, O. 24 should be Y. 3 should be D. All right, so we keep going through this, and I'm going to kind of pause here and just say, okay, I'll figure out the ones I need to for what I'm encoding here. So we want to use this to encode the message yeehaw. So the ones that I need for sure, right, would be figure out this, Y, E I've already done, H, A, and W. So I'm just going to say, yeah, I don't really need to do more work than is necessary, but again, it's not that hard to fill these out. Okay, so let's find W. So we said W was 22, which becomes 6. We find 6 over here. Oh, that's G. Okay, so that's going to be G. And then Y was 24, but it became 16. So we find that. We go, oh, that's Q. Sweet. So now if I want to encode the message yeehaw, then I've got Y is going to become Q. E is going to become U, so I have 2 U's. H is going to become J. A is going to stay A, and that is actually true of any key here. And then finally W becomes G. All right, so here's our new encoded message. All right, now suppose someone sent us the message GODD, QSW, etc. We are supposed to decode this thing. Well, we have some of these letters, right? So we have G, which was actually W, O, which was actually I, D, which was actually L, so we have 2 of those, will, Q, which we found here, was actually Y, S, so far we have not found that. So probably we should go through here and just finish these out, at least until we find S. So, all right. N actually stays N, right? It was 13, it stays 13. So we go, okay, that's N. O becomes 18, whatever 18 was, which is S. Oh, there's our S. So maybe I can pause for a minute and see how far this gets me. So S, if I see that in an encoded message, is really O. W, if I see that, I do not see that in here, so we'll figure that one out. Right, so we keep going. I'm actually going to fill out this bottom row just through the magic of editing here, and then we'll carry on. All right, so W, now we find that down here, and we say, okay, originally that was U. I, we find that down here, that was M. A stays A, we said. H was originally R, so I have 2 of those. Q was Y. Will you marry? Interesting. I was originally M, and U was originally E. Will you marry me? I'm not sure why you want to send that encrypted, but you could. So I don't know. Maybe this is like some Shakespearean thing. You got to send that message encrypted. Okay. So you can do this by hand, right? You can go through this entire process. The other thing you can do is use a decryption value. So for example, we use the key k equals 5. So someone could go through and follow the exact same process for encryption, but instead use the decryption value 21, and it would spit out your, basically give you what these letters should become. So it's kind of like working backwards. And that's something that I'll have you do on, again, this would be something you could sort of work through, figure out same way with the encryption, and I'll give you a template for the project and for the homework.